So here's what we know is that based on what we talked about last time, to find the equilibrium constant, we need to know the equilibrium concentrations of all the substances involved in the reaction. Because we had to know those concentrations, and we had each of the concentrations, the ones on the right side on top, the ones on the left side on the bottom, each of their concentrations raised to their coefficient power. But if we didn't know one of those equilibrium concentrations, then we really wouldn't be able to find the equilibrium constant. But oftentimes, if you're doing a reaction, is that you generally know how much of each thing you put into the reaction, but don't often know how much you end up with. You need some way of, you've got all these things mixed up in your reaction vessel. So you put them on to start with, they all react, they reach equilibrium because you have a reversible reaction, but it's sometimes very difficult to measure each one of them, what their concentrations are at the very end. And so we do have a method, though, we're going to talk about here, that if you know just one of the final concentrations, that tells you what the change in concentrations of one of your reactants, one of your substances that you're involved in this reaction here, then you can use that to find the others. And the reason why is if you know one of their changes, you know that in any reaction, the change of one is in mole ratio to the changes of all the others. Remember all those coefficients out there. Those coefficients basically tell you what the mole ratio is. If you have a 2A plus B yields 3C, then you know that since it's 2A plus B, that you need twice as much for A than you do for B, and you need 3 times as much for C than you do for B because it was 2A plus B yields 3C. This mole ratio is going to let us figure out what the final amounts are if we know all the initial amounts of what we start with here. So, an example here. So, if the reaction that we have down at the bottom of 2NH3, reversible reaction to N2 plus 3H2, if we know that the concentration of N2 of nitrogen increased by 1.5 molar, then we can find the concentration of the other two. Because if we know that this N2 right here increases by 1.5 molar, let's take a look at the NH3. Well, what's the mole ratio between the two? N2 is 1, this one's 2. That means that for every 1 mole of N2, we need 2 moles of NH3. And if we used up 1.5 moles of N2, that means we had to use twice up. We had to have a change of twice as much of NH3. And so that means we know we had a change of 3.0 molar was the concentration change for the ammonia. And for the H2, for the hydrogen, it would be 3 times as much because it has a mole ratio of 1 to 3 right here. And so that's a 3. And so that means we'd have 4.5 molar would be the concentration change of the hydrogen here. And so that's how you go about figuring out concentration changes. It's a little difficult, once again, to explain this by talking about it. Let's work out an example, and that'll give a little better indication on how that works. So let's take a look. So just as a note, the technique that we're using to determine this is called the mass action expression. The mass action deals with our calculation for KEQ, and we'll use a particular technique here that'll help us out. So we are told here 3 moles each of gaseous carbonic acid are placed in a 6-liter container. If the decomposition reaction is reversible, and 1.2 moles of CO2 are found after the reaction reaches equilibrium, what are the equilibrium concentrations? So here's basically the way this works. The first step is, if it's not written out for you, write out the chemical equation, same as it has been on stuff before. And so it's decomposition of carbonic acid. Carbonic acid, this is the one we've dealt with a lot on these things right here. So H2CO3 is what that is. It's a reversible reaction. So we have the double-headed arrow on this. And carbonic acid decomposes into carbon dioxide and water vapor. Let's look at what we have for our coefficients. We have 2 hydrogens on one side, 2 on the other, 1 carbon on the left, 1 carbon on the right, 3 oxygens on the left, and 3 on the right, so we're already balanced. And so the first thing you want to do whenever you're setting up one of these mass action expressions here is you're going to write down 3 sections here. The first section you're going to be dealing with is basically going to be your before section. And so we'll call it a B for before here. Then you're going to have your change, and then you're going to have basically your final down here. And what we know is if you take the before and add the change, that'll give you the final. All right? So let's write down what we know. Is we have 3 moles each of gaseous carbon dioxide. And so really it shouldn't be each, it should be 3 moles. So get rid of that each right there. We don't like that anymore. So 3 moles of gaseous carbon dioxide, gaseous carbonic acid are placed in a 6-liter container. What you want to write down for each of these is you're going to write down the concentrations, because we're really not interested in how many moles. We're interested in what the molarity is, the concentration here. And so if we have 3 moles in a 6-liter container, that's going to give us a molarity of 0.5. So we started off with a carbonic acid with a molarity of 0.5 here. And that's what we start with. Now it says that this is what's placed in here. So how much carbon dioxide we placed in originally? Didn't say we placed any, so we don't have any carbon dioxide to start with. What about water vapor? Did we place any water vapor to start with? Nope. And so to start off with, and this is normally how we start reactions, we don't put everything in there, we just put things on one side. So we put carbonic acid in here. And since this is a reversible reaction, this reaction will start off by flowing to the right side, and so that the concentration of carbonic acid decreases, the concentration of the carbon dioxide in the water is going to increase. But how much? Well, we know that there are 1.2 moles of carbon dioxide are found after the reaction reaches equilibrium. So if we were to look at sort of our final amounts here, we know that afterwards there are 1.2 moles of carbon dioxide, but we don't want moles, we want molarity, concentration. So we take our 1.2 moles and divide it by the size of our container, which is 6 liters. And so that's 0.2 if you do that math here. And so we know we end up with 0.2 molarity concentration of our carbon dioxide. And this is all we know right now. So we say, what are we going to do here? Well, we could find one of the changes, because for the carbon dioxide, we know the original amount, which is the 0. We know the final concentration, which is 0.2. And so we know the change in this one had to be plus 0.2. We know that's the case. But now that we know the change, here's where the magic comes in. Because of the fact that the change of the carbon dioxide is 0.2, we know that change is going to be in mole ratio with all the other ones. And so the coefficient of the carbon dioxide is 1. It's not really there. And the coefficient of the hydrogen, the water is 1. And so there's a 1-to-1 mole ratio between those two. And so that means that if the carbon dioxide gained 0.2, it means the water has to also gain 0.2. Right? And the mole ratio of the carbon dioxide to the carbonic acid is also a 1-to-1 ratio, because they both have coefficients of 1, which means that the mole ratio between those two also has to be 0.2. But since the reaction goes from left to right, the carbon dioxide and the water vapor were gaining, the carbonic acid was losing. And so instead of gaining 0.2, it's going to lose 0.2. And if this one right here loses 0.2, then this lets us now go ahead and figure out what the final concentrations, the equilibrium concentrations are all of. And I called it a final. It really should be an equilibrium concentration down here. That's what I probably ought to call that. So with the carbonic acid, it started off at 0.5 and it's lost 0.2. So now its concentration is 0.3 molar. So I've got that. The carbon dioxide, I already knew what its concentration was. It was 0.2 molar. The water vapor, or the water, it is water vapor because all these are gases in this case. 0 plus 0.2, I get 0.2 molar are my concentrations. So the question is, what are the equilibrium concentrations? These are them right there. I have 0.3 molar carbonic acid, 0.2 molar carbon dioxide, and 0.2 molar water. And so those are the concentrations I have of each one of these at equilibrium. If I wanted to find KEQ, I can now do that because I now know what all my equilibrium concentrations are. That's basically how you're going to set up one of these moving to equilibrium type problems. What if you're missing more information than what we've lost here? Is that what if we know the equilibrium constant and we know the initial concentrations, but we don't know anything about the final concentrations? We lack all that information. If we don't know the final concentrations, then it really sort of puts us a little bit in a little bit of a difficult position, because without the final concentration, without those equilibrium concentrations, we can't find the change. And without the change, then we can't find the other changes. And so then we can't find any equilibrium concentrations. And so using our previous method, we're sort of stuck. But there is a little mathematical trick that we can use, using some approximations that work under the case that if KEQ is very large, over 100 or so, roughly, it needs to be large, and the reaction starts on the right side of the reaction. So if KEQ is large and the reaction starts on the right, we can use this trick. Or if KEQ is small, like less than 10 to the negative third, and the reaction starts on the left. So if KEQ is big and the reaction starts on the right, we can use this trick. Or if KEQ is small and starts on the left, we can use this trick. So in this method, The changes in concentration are written in terms of an unknown, x, because we do not know what the final concentration is, the equilibrium concentration, so we can't find numbers for any of the changes, but we can write them in terms of our unknown x. And this variable will be substituted into the equilibrium constant equation. So we're going to basically find what the equilibrium concentrations are in terms of x, then put it into KEQ, and then solve for x for there. So solving for x lets us determine the equilibrium concentrations then.